And welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. Today we will continue our discussion of the response surface and specifically focus on the central composite design. So let's take a look at that. As we saw in the last lecture, the central composite design has three different parts to it that we have to consider: the cube points, the axial points, and the center points. And we're going to discuss all of those and see how they work together to fit a response surface to our data. We're also going to consider two other response surface designs, the Box-Behnken design and the uniform shell design. These are both different ways that we can choose points in a space, in design space, to fit a response surface. So how do they all work and which one's the best? Well, we're going to find out in today's lecture. And welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. Today we're going to continue our discussion of response surface methodology. Specifically, we're going to focus on the central composite design, which we introduced at the end of the last lecture. So as I mentioned last time, response surface methods are used to optimize some type of industrial process. The goal is to maximize or minimize some number, some response that we're collecting from our process, whatever it is. So the idea, right, is that we have to pick points very carefully, as I mentioned, in our design space in order to optimally optimize in a way, right? We want to be able to find our optimum, and we don't want to waste a lot of time picking just random data points like other optimization methods. And what we're going to talk about today is how the different pieces of the central composite design all kind of play a role and allow us to fit a response surface to our data. So let's get into the notes and dig into this idea of a central composite design. So we're going to be discussing today the central composite design as we discussed in the last lecture. So the central composite design, if you recall, is made up of three types of points, which are going to be the center. Those are the ones where xi is equal to 0 for all I. Remember, we've encoded our variables, so we're going to just be able to take on values like 0 and plus or minus 1, where in reality they might correspond to different temperatures or pressures or other inputs to the system. We have the cube points, where xi is going to equal plus or minus 1 for all I. And lastly, we have the axial points. xi is going to equal plus or minus alpha for some I, and xj is equal to 0 for all j not equal to I. And as we drew last time, if we look at these on on two dimensions, so if we have two inputs to our model, x1 and x2, then what the design will look like will look a bit like this. We're going to have our center points in red here. We're going to have our cube points, I guess in this case square points, but they're just referred to as the cube points, in green. And we're going to have our blue axial points for some value of alpha, typically between 1 and usually root k, and we'll talk about that a little bit later, but usually greater than or equal to 1. All right, so these are the three different types of points, and we have to figure out now why we need all of these different types of points for our design. And we have to also remember, what are we trying to fit, right? If we have a response surface, we have something that's going to look like yi is going to be, well, what? It's going to be beta naught plus the sum I from 1 to k of beta I xi. Then we're going to have the cross terms, the interaction terms, I, well, we'll say I less than j, beta ij, xi, xj. And lastly, we're going to have our pure quadratic terms, I from 1 to k, beta I xi squared. And then there's going to be some epsilon random noise. I probably shouldn't have written y there, I. Right, so the idea is that we have some inputs x, we have an output y. It's really just a linear model. Yes, things are cubed or squared in this and multiplied together, but in a sense, you can think of this as just one big linear model that you can use least squares estimation to fit, assuming you have data points that allow you to estimate all these terms. So what I want to do is consider an example. We're going to do an example for k is equal to 2, which is basically this picture that I drew up here. And if we really want, what I can do is I can kind of connect the cube points here just to maybe make the picture look a little nicer, something like that. All right, so what is our design going to look like? So what I want is I want to write out the design matrix. So the design matrix here is going to be, well, it's going to have a couple things in it. First, what I'm going to have is I'm going to have an x1 and an x2. These are the two variables that I'm setting. Remember, they could be temperature and pressure. They could be other things that we are changing. I always just go to temperature and pressure because a lot of the articles that I found when I was looking up uses for response surface seem to be about extracting oil from various things like almonds or other things like that. And it always seems to be like, what kind of temperatures do we need? What kind of pressures do we need? What kind of humidity or otherwise do we need? But for now, they're just going to be two generic coded variables. Now, remember, there's going to be a couple different points we have. There's going to be the center points. So this is going to be, we'll call this is center, to kind of keep with my color coding here. And then we're going to have our cube points. Now, there are 4 different cube points here to consider. There's going to be the 1, 1, 1, minus 1, minus 1, 1, and minus 1, minus 1. All right, these guys are going to be our center points, or sorry, cube points. It's all C's. I also mentioned in the end of last lecture, we often like to replicate the center point more than once. We're going to talk about that a little bit later in this lecture. For now, we're just going to include it once in our design matrix, or a design, so we don't have to, also I don't have to repeat just a bunch of zeros. And lastly, we're going to get axial points, and in this case, we're going to have 4 of them. These are these 4 blue points here. And when we have the axial points, we're going to have, for some value of alpha, we'll have alpha 0, minus alpha 0, 0 alpha, and 0 minus alpha. So this is what the inputs to our central composite design for k equal to 2 would look like. And again, we might replicate the center point at 0 a couple more times, but roughly this is it. These are all the points we have. In this case, we have 9 of them if we include axial and a single center point. If we replicate the center point, then we might have 10 or 11 points. But we're not completely done yet in the sense of filling in this table. Notice this horizontal line is extending out kind of far because x1 and x2 are going to allow us to estimate the beta I, beta 1 and beta 2 in this case, but we also have to consider the cross terms. So the cross terms, well, what are they going to look like? If we multiply x1 by x2, well, for the center point, we're still just going to have 0. Then we're going to have a 1, a minus 1, a minus 1, and a plus 1. So if you kind of see what happens when we go from these columns to the interaction column, we're basically doing that XOR operation again. If the two values x1 and x2 agree, we put a 1 in this column. If they disagree, we put a -1 in this column. So this should look really familiar. It's basically a 2 to the 2 factorial design. I'll hide that over here in green. This, or maybe in black to make it stand out, this is a 2 to the 2 factorial design hiding within our response surface. So the central composite design actually has a 2 to the k or something like that factorial design within it, and those are going to be the cube points. Now, when we look at the axial points and we multiply them together, well, we just get a bunch of zeros. So remember, when we're trying to estimate parameters in a linear model, we have to make sure that the columns, I guess, of the design matrix, we need to make sure that they are all orthogonal, or not necessarily orthogonal. We need to make sure they're linearly independent of each other, or else we can run into trouble because we won't be able to solve we won't be able to invert the design matrix. So that's where we have to just be a little bit careful, and that's where all of these points are going to come into play, because the last thing we have are the pure quadratic points. And the pure quadratic, x1 and x squared, or x1 squared and x2 squared, well, it's going to be 0, 1, 1, 1, 1, and 0, 1, 1, 1, 1. So if we don't, let's pretend we don't have those axial points, we have a problem here. The column 0, 1, 1, 1 is repeated twice, and that means there's a linear dependence in the design matrix. If I were to just cover up, I'm going to cover it with my hand. I can't cover it on OneNote here, but if we were to just forget about those axial points, we would not be able to estimate these quadratic ones, because when you see two columns that coincide with each other, that means they're confounded. That means they are perfectly correlated with each other, and that means we can't estimate both of them separately. If we estimate them, we're kind of estimating them together, right? They overlap. But because of the axial points, we have 4 more rows to add in. We have an alpha squared, 0, 0, and we have a 0, 0, alpha squared. And now these two columns are different, and that means that we can estimate them. Because ultimately, right, this thing here, if we take this entire matrix, this is going to be the design matrix X, and ultimately we want something like beta hat is equal to X transpose X inverse X transpose Y, right? Where in this case, X is this big matrix, and beta hat is going to be our we would also, I guess, need a column of all ones or something for the intercept. Let's forget about the intercept for a second, so that we can just work with this thing, right? And what we would have is something like beta 1, beta 2 hat, beta 1 2 hat, beta hat 1 1, and beta hat 2 2. So again, this is just trying to estimate my 5 parameters in this model, ignoring the intercept because I didn't include, technically the design matrix would need a column of all ones to correspond to the intercept, etc. But I didn't include that in this setup. Regardless, this is what a central composite design for k equal to 2 would look like. We would have, in this case, 9 rows. 10 or 11 if we replicate the center point. And these would be what the columns all look like. And these columns are what's going to allow us to estimate each of these parameters individually. So let's take a little bit of a closer look at this. So what do we need? Well, first of all, we need to figure out the right choices for a couple things. So for the center points, they're kind of the easiest. Center points, we're basically done. There's nothing else to do except determine how many times to replicate. So how many times do we replicate? Well, there's not an exact answer to that. The recommendation that I think you can find in textbooks, recommendation, is between, let's say, 2 and 5 times. The more times you replicate the center point, the better estimate of the variance you're going to get. So things will be a little bit easier to work with. You'll get, I guess, a better sense of the noise in your design. That is, if you repeat the same point over and over again, now you have replications with the same input values, and you can treat them all, if you can imagine them to be independent replicates, then we can use that to compute the variance. And we always assume that our epsilon, that variance, that noise term up here, is going to be IID. So no matter where we move in our design space, the variance will always be the same. Now, that's not always true, of course. Sometimes when you change your inputs, the variance may increase or decrease, but we have this simplifying assumption that we work with in this framework. So yeah, basically there's no right or wrong answer. The wrong answer is 0, and I guess maybe 100, because we don't want to replicate this too many times, because presumably every data point we collect is going to cost time and money. So we don't want to have tons of replications at the center point. We don't really need to, but we would take a few. Like I said, usually between 2 and 5 is what they recommend in the textbooks. Now for the axial points, this is almost done, in the sense that we have to get 2k of them for the quadratic terms. Because if you look back at this design, what do we have here? Well, we actually have, if we just look at x1 here, we have 3 points in a row. And if I have 3 points in a row, I have a 3-level factor. So if we kind of just stare at that, we have, we're not doing all the 3 cross terms, but in a sense, I need basically, we need minus alpha 0 and plus alpha to get a quadratic contrast. So remember what we talked about when we did 3 to the k factorial designs? Because I have 3 factor levels now, I can go beyond just looking at, well, is one level bigger than the other? Is there a linear change? I have 3 points, which means I can get quadratic changes. I can see if it goes down and then up. I can see if it goes up and then down. And that's why we need to have, well, a plus or minus alpha for every axis, and then of course the center point as well, so that we can get these 3 levels, so that we can estimate the quadratic pieces in our model, that is the pure quadratic terms. This is for estimating the beta II terms, or parameters, I guess is the right word, but terms is kind of my generic word. Yes, so that's where we need these, and then we just need to choose, and we need to make one choice, so we need those, and we need to choose a value for alpha, right? So what should alpha be, right? We're just kind of stretching out along the axes here in direction plus or minus alpha. So then the question is, well, what should I make it? Should I make it 1? Should I make it 2? Should I make it 50? What would be a good choice for alpha? In this case, usually, alpha is going to be somewhere between 1 and the square root of k. And then we have sort of two subpoints. If alpha is equal to 1, then all design points are on the cube, or the hypercube, I guess. In this case, what we would have is something that looks like dot, 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 dot. So in that case, we would have all of our points would lie, except for the center point, which is always in the center, obviously, but all of our non-center points would be on the cube. And if we took this into higher dimensions, it would all be the same. All of our points would be on the k-dimensional hypercube. If alpha is equal to the square root of k, then all design points lie on the sphere, or I guess the hypersphere in k dimensions. If we draw that in 2 dimensions, which is easier for me, we would have something that would look like this, and then we would have points here, 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 and here, a distance of root 2 from the center, and we can think of these as all lying on the same sphere, or the same circle in 2 dimensions. If we were in 10 dimensions, we'd have some 10-dimensional sphere, and all of our design points would lie on the surface of that sphere. And then any alpha in between is going to be, well, somewhere in between that. So there are some reasons to choose one or the other. So we have choose alpha equal to 1 if changing the factor levels is hard, i.e., only need x equal to -1, 0, and 1 instead of x, let's say xi equal to minus alpha, -1, 0, 1, and alpha. So there could be a reason why we don't want to have to keep setting the dials on our machine, and we'd rather just have 3 different settings to test rather than 5 different settings. That's one reason why we might choose alpha equal to 1. Now, if it's not a problem to have more than 3 different settings for our machine, we would probably want to take alpha to be slightly bigger than 1, as we typically get a little bit more coverage, right? The circle kind of, or the sphere kind of bulges out a bit, and our points are a little bit more spread out in space, and that's going to allow us to get more information about our response surface. So what we'll say is choose alpha greater than 1 for better coverage of the response surface. See, it's an interesting problem because in some sense we want to spread out our points so we can see more diverse points to get a sense of what the response Y is doing. On the other hand, if we spread them out too far, it's going to be so noisy, we're not going to be able to figure anything out. So there's kind of a trade-off here, and it's really going to depend on the specific setting in which you're running a response surface as to, well, what you want to do. If you want alpha to equal 1, if you want it to be bigger than 1. If you have a spherical design, well, another thing to note is if alpha is equal to root k, we have a spherical design as noted above. Spherical design, but must include center points, or else the variance, not the variance, sorry, the estimated variance. The variance is going to be whatever the variance is, but the estimated variance in this case will be infinite, and that's bad. But if we have center points, then it's not going to be infinite because we can replicate those center points to try to control the variance. So basically, the bigger alpha gets, the more wild the variance, the more unstable the variance becomes. But if we replicate the center point, we can sort of recover that stability. So typically, so I'll say, i.e., bigger alpha means more center point replicates. So for example, if it's really expensive to collect data points, if you don't want to have to keep changing your factor levels, you probably want to set alpha equal to 1. If, on the other hand, it's easy to collect lots of data points, you probably want to set alpha close to, if not equal to, the square root of k, have a spherical design, and just make sure to keep sampling those center points to make sure that the variance is going to be stable enough. And we'll look at this when we look at an actual response surface data set later in probably the next lecture, not this lecture. We'll have a central composite design, and we can see what happens when we throw out some of the points and what happens to the variance and things like that. Now, the most important, maybe not the most important, but one of the key points is going to be one of the key things is figuring out how to choose the cube points, because if you recall from up above, before we went into this long discussion on axial points, the center points, well, that's easy. We just replicated a few times, we're done. The axial points, we have to figure out what alpha should equal, and there is some reason to choose one or the other. Now, when we get to the cube points, basically, we need to pick a 2 to the k minus q design. And now we're going to bring in what we discussed about factorial designs back in the binary case, multiple lectures ago, because we have to be really careful with what kind of design we choose, right? The goal is we want to choose the smallest possible fractional factorial design, because we don't want to sample points that we don't need to sample. But if we don't choose it carefully, we're not going to be able to estimate all of our betas, and that's going to be a problem. So how do we choose the fractional factorial design component? All right, so we're at the final part of the central composite design, and what we need to do is figure out how to choose the cube points, because like I said in the last lecture, basically a central composite design, CCD, has on the order of k squared parameters. But a 2 to the k design has on the order of 2 to the k, it is 2 to the k data points. So the conclusion is that running a 2 to the k full factorial design within the central composite design, CCD, is too much. That's the qualitative hand-wavy way to say it. More mathematically, I'll say, i.e., we only care about two things: main effects, which in this case are the beta I, and two-way effects. which are the beta I, beta j. Now, the pure quadratic pieces can't be estimated from the cube points, but we already have those being estimated up here by the axial points. So that's done. And the cube points are going to allow us to estimate the main and interaction, two-way interaction effects. So what we have to do is we have to basically, well, the point is, first of all, we only care about main effects and two-way interactions, and we don't need any higher order interactions. So all those three-way, four-way, K-way, whatever, we don't need them. They're not going to matter at all when it comes to fitting the response surface to our data points. So we have to pick a design that's going to be the smallest design possible. We basically pick the smallest 2 to the k minus q design, i.e. largest q, such that all beta I and beta ij are estimable. So how do we do that? Well, there's an easy answer. The answer is pick a resolution 3-star design. And then the question is, what in the world is a resolution 3-star design? Well, this is a resolution 3 design with no entries in the defining contrast subgroup being of length 4. So what's going on here? Well, the first thought that you might have is I want to make sure I can estimate all of the main effects and all of the two-way interactions. So that means that I would need all of the main effects to be clear. I don't want them aliased with any one or two-way interaction. And I need all of the two-way effects, interactions to be clear. I don't want them aliased with any one or other two-way, because if a one-way or a two-way, if one of these is aliased with another, then I can't estimate the betas separately. So I need to make sure I can estimate all of the betas separately, which means I don't want any aliasing of that type. If I have a resolution 5 design, why don't we just put that in here? The easier, weaker answer is a resolution 5 design as all main and two-ways will be clear. In the case of main effects, they'll be strongly clear. But the resolution 5 design is actually overkill. It's including too many data points. In fact, we are allowed, I'll say, in fact, we can allow for aliasing between a main effect and a two-way interaction, because of the axial points. Because the axial points will, I guess, de-alias these. So because we have the axial points, remember the axial points stretch out along, well, the axes. And if we jump back to the very top, that means that we have extra information about all of the main effects because we actually don't need any cube points to estimate the main effects because we have 3 points in a line. And if we have 3 points in a line, that means we can estimate a main and a quadratic effect for each of x1, x2, and so on, but we can't get any interactions. The cube points are going to give us the interactions, and they're going to give us more information on the main effects. But, and here's the key thing, we're allowed to alias a two-way interaction with a main effect, but we can't alias two-way interactions. And the reason comes back to this design matrix. The idea is that if I have a two-way interaction, well, I don't get any information on the two-way interaction from the axial points. I just get zeros down here. It's always going to be zeros. So I really need the cube points to get all of my two-way interactions. In this case, I only have one of them, so there's no fear of aliasing. But if I had more of them, I would have to be really careful that I don't have them aliased with each other. Whereas if I have, say, x2 or something aliased with x1 crossed with x2, I can use the axial points to de-alias them, because the axial points are different between the main effects as they are with the interaction effects. And that's where that'll save you. And that's why we can actually become much more efficient than we otherwise think we would be. At first, like I said, and the easier or naive answer would say, let's just do a resolution 5 design, but that's too many points. In fact, we can have a resolution 3 design, but with the star, and the star is giving us the key criterion that we can't have any length 4 terms. And I'll say note, a length 4 term in the defining contrast subgroup will alias pairs of two-way interactions. And that is bad. We don't want that to happen, so we have to avoid length 4 terms in our defining contrast subgroup. So that means we can do this, right? We can actually pick a nice design and just make sure that we don't have any length 4 terms, and that will allow us to fit our central composite design, right? All right, so that is more or less, I think, everything we need to do about a central composite design. Now we've kind of dug into all of the different reasons for each of these data points. So we can also talk about a few other designs, but first I just wanted to give an example of a 3-star design. So let's do an example. Let's say we have, I don't know, how many inputs should we do? I'm doing this off the top of my head. So let's do 5 inputs, a 2 to the 5 minus q design. So right off from the start, we don't want to collect 32 data points if we had q set to 0 for doing a full design. Instead, what we want is our resolution 3 design, 3-star design. So let's say with factors 1, 2, 3, 4, and 5. Just to give me something to work with here. Actually, maybe I'll do A, B, C, D, just because I like the letters better. A, B, C, D, and E. All right, so what can we try to put into our defining contrast subgroup? Well, again, we're allowed to have words of elements of length 3. We can't have 2. That would be bad. That means 2 main effects are aliased together and everything falls apart. You generally never want a resolution 2 design, like, ever. At least I can't imagine any situation in which you would want one. But in this case, yeah, we can at least do this, ABC. Now there's actually a bit of a problem, because in this case, if we try to include another length 2 word, we could try something like BCD, but that means that the other term aliased with the cross term, right? The other term aliased inside the defining contrast subgroup is going to be AD. So that's bad. That's no good. So what we could do is we could try something like instead of BCD, we could try CDE. But this is also going to cause up trouble, because if we do this, then the other term is going to be A, B, D, E, and that's also bad because it has length 4, right? This is bad because we would have resolution 2, and this would be length 4, so it's not going to be 3-star anymore. So that's no good. So what that really means is that we actually can't do we could have a 2 to the 5 minus 1 design, but we could also, in this case, just take A, B, C, D, E, and then have a resolution 5 design. So in this case, there is no really good 3-star design. We could have a resolution 5 being with a single term in our defining contrast subgroup being the 5-way term, or we could pick a 3-way term and have a resolution 3-star. But both of these are going to be 2 to the 5 minus 1. So in this case, you're not saving anything by going to a 3-star design. However, what if we were to try a 6-level factorial design? So let's do another example. 2 to the 6 minus something. All right, well, now, again, what we could do is we could include a single word of length 5 or 6. So we could just do an AB. Well, I'm not going to do that one yet. What we could do is we could do a word of length 5, A, B, C, D, E. And this would give us a resolution 5, 2 to the 6 minus 1 design, and we'd still need 32 data points. So that's not ideal. But what we could also do is something like A, B, C is equal to D, E, F is equal to the cross term A, B, C, D, E, F. And now we have a resolution 3-star design, and this will be a 2 to the 6 minus 2. So now we only need 16 data points, right? This would be 32, and this would be 16. So we can get away with just collecting 16 of our cube points. Remember, we're starting with a 2 to the 6 design, that's 64. So we can actually cut it down to a quarter of the total number of vertices on the hypercube. That is, we can take 64 down to 16. We can save a bunch of data points, right? We can save the time and energy and cost it would be to collect all those data points and still be able to fit our response surface. So in this case, the sample size n would be, well, the number of center points, which I'm going to call C, plus 2 times 6 for the axial points, plus 16 for the cube points. And what I end up with is, I guess, 12 plus 16, which is going to be 28. So we're going to say 28 plus however many times I replicate the center point, which is much, much better than, say, starting with 32 or 64 points. And that's where the 3-star design can kind of save you. Again, if you're in most of these examples, when we have K being small, like here, the resolution 5 and the 3-star design are going to be the same thing in the same number of data points required. So there's really no difference. In that case, I'd probably just do the resolution 5 design because, hierarchy principle, might as well just alias the largest thing you've got with the identity. But down for the 2 to the 6 design, there is a definite savings in using a 3-star over a resolution 5 design. All right, so that's basically some examples of how you could run a response surface, a central composite design. But the thing is that we could consider other types of response surface designs beyond the central composite design. And that's what we're going to talk about in the last part of today's lecture. All right, so the central composite design is kind of the main response surface design we're going to consider because it's really nice in the sense that it takes some of the knowledge that we've gained about the 2-level and 3-level factorial designs and fractional designs and puts them into a context where we can use them for response surface methodology. But there are other ways to choose points for a response surface, and we're going to discuss a few other examples. So the first one that we will discuss is called the Box-Behnken design. And we'll just block this off because we have a new type of design. So what is the Box-Behnken design? Well, the idea is that we want to combine factorial designs with a balanced incomplete block design. So this is a cross between I think it's a 2 to the k design and the balanced incomplete block design. So this is kind of fun in the sense that it takes 2 different designs that we talked about earlier in the course and cramps them together into one super design. All right, so how in the world do we actually do this? So the idea is to start with a BIBD and then replace each block with a 2 to the k design. All right, so that might not be immediately clear what I mean, so let's do an example. Well, the example that I have is going to start with, we're going to have 6 blocks and 4 factors. So 1, 2, 3, 4, 5, and 6. This was the same one I think we did lectures and lectures ago. A, B, C, and D. All right, so what we're going to do is we're going to sample, I'm just going to use stars to say we sample these points, and then we don't sample those points, right? Every block is going to have 2 factors in it, or 2 factor levels in it, because here we would just have A, B, C, and D would correspond to different levels of the same factor, but we're going to end up making them different factors in our response surface. So it's a little confusing, but for right now, right, every block is going to have, if we go back to the discussion that we did lectures ago, every block in this example is going to have 2 treatments, and every treatment is going to appear in 3 different blocks. And every pair of treatments is going to occur in exactly 1 block. So in this case, right, I have A is paired with B, B is paired with C, and C is paired with D in blocks 1, 2, 3. Then I need to have A paired with C, and I also need to have A paired with D, and I think the missing one is B paired with D, which is this one. B paired with D. So we have this nice little pattern here that looks like that, right? This is our, just to put in all the information here, right? This is our BIBD, and it has T is equal to 4 treatments, B is equal to 6 blocks. Oh, I forget the notation now. I think it was K. I'm going to try K. K is 2 treatments per block, and R is going to be 3 blocks for every treatment. And hopefully I got that right with the notation from chapters in my notes ago. All right, so then the idea of turning this into a Box-Behnken design, named for presumably Box and Behnken, back in the 1960s. Well, the idea is that I'm going to take one of these blocks, right? So I'm going to take block 1, and what I'm going to do is I'm actually going to insert something that's going to look like this. So it's going to be A, B, C, D. And in this case, we're going to insert, because we have 2 factors here, A and B, we're going to insert a 2 to the 2 design. So I'm going to get a 1, 1, 1, minus 1, minus 1, 1, minus 1, minus 1, and then zeros elsewhere. So basically those green, the green box over here becomes this green box over here. So is that kind of clear what's going on? I can start to write this all out. I don't really want to write out all, 4 times 6 being 24 rows, but effectively what we would have is something that looks like A, B, C, D. And then the first 4 observations, Y1, we'll say 2, 3, and Y4, is going to be exactly this green box. 1, 1, minus 1, minus 1, 1, minus 1, 1, minus 1, 0, 0, 0, 0, 0, 0, 0, 0. And then what are the next? So do you see what the next 4 observations or entries in our table should be? Well, the next 4 entries are going to be, again, 1s, 0s, and minus 1s, but corresponding to the center 2, B and C. So now A and D are going to be set to 0, like this. And now the center 2, B and C, are going to take on the values of 1, 1, minus 1, minus 1, 1, minus 1, 1, minus 1. And then so on. The next thing we would do would be to do C and D together. So I'm not going to write it all out, but the next thing we would have is zeros, and we would have like a 1, 1, and so on. Right? So trying to color code it to hopefully make this a little bit clearer, we would have the first block, the second block, the third, and so on. So again, they're not actually blocks in our response surface design. We're turning each of the blocks in our BIBD into a 2 to the 2, in this case, factorial design. If K here were equal to 3 or 4 or 5, then we would have a 2 to the 3, 2 to the 4, 2 to the 5 design. I think in that case, we'd probably want to start thinking about fractional designs. But to be honest, I haven't spent a lot of time looking at the finer points of the Box-Behnken design. The idea is just that we can choose points in this special way, and it will allow us to fit a response surface model to it. So in this example, we'll say a total of 24 data points. All right. Okay, so is there anything else interesting about this? Well, I guess there are a couple kind of interesting things. Note all points, design points, lie on the faces of a hypercube, i.e. only need xi to take on the values of -1, 0, and 1. So similar to the square design that we talked about up above for the central composite design, in this case, we only need to have the xi's taking on the values of -1, 0, and +1. So again, if for whatever reason you don't have the ability to keep changing the factor levels to lots of different factor levels, this allows you to only choose 3 rather than 5 or more. So that's, I guess, one nice thing. That's right. Also, oh yeah, there's one other thing I forgot to note. Still need to replicate some center points. Almost forgot that. In basically all of these response surface designs, including the next one we're going to talk about, we always need to replicate some center points just to get a handle on the variance of the response surface data, I guess. All right, and then there's one other thing to note, and that is there is a property here called orthogonally blocked. Basically, this design is orthogonally blocked. All right, so what does that mean? Where it says this is the case where the block effects and the parameter effects are orthogonal, and hence do not interfere with one another. So basically, block and parameters are orthogonal, i.e. do not conflict with each other. All right. So, yeah, basically that's it. There's nothing really much more to say other than I can arrange my points this way because, again, remember the intuition we had from the central composite design, because we have each of our factors here is taking on 3 values in a row. That's going to allow us to compute the pure quadratic terms. So that's going to be important, right? We need to make sure that we have those 3 points in a row so that we can get our pure quadratic terms. Otherwise, we have a bunch of plus or minus ones, so we can get interactions. Remember, every pair, and this is another thing, remember with the balanced incomplete block design, there's a lambda. In this case, lambda is equal to 1, which means every pair of factor levels occurs once in one block. And that's good because that means that we can figure out how A interacts with B and how B interacts with C and how A interacts with C and C with D and so on, right? If we didn't have that nice balance condition, we wouldn't be able to get all of the interaction terms out. And yes, I think that's all the interesting points, except, typically the total number of treatments will become quite large as the number of factors increase. So this design becomes inefficient, i.e. too many data points as, I guess, the number of factors increases. So typically, I guess the recommendation that you can find in the textbook is that if you have a large number of factors, you probably don't want to do this because it's going to be inefficient, right? You're going to have this number of blocks in the BIBD times the 2 to the k factorial, it can grow quite fast. All right. And another design, also this one is, I guess, was from the 1970s. And the last design, I think, if I'm correct, we'll talk about today, is the uniform shell design. If I can spell that right. Uniform shell design. And this was from the 1970s. Yeah, a lot of these are actually quite old. I guess this one, Box-Behnken, was 60s, uniform shell design is 70s. I'm not sure if I found out when the central composite design first came about. I have in a theorem from 1959. So yeah, a lot of these methods date to like the early second half of the 20th century. But there is still some research going into these today, though a lot of it's how to use them in practice. And if you want, you can find articles that I posted to the class webpage where you can see how people actually use some of these designs for in actual industrial processes, which is quite interesting, I think. I find these quite kind of fun to think about. Right, so we have one more to talk about, the uniform shell design. This one is maybe the easiest to think about. Basically, given k factors, x1 through xk, we take k squared plus k points, design points, and uniformly spread them out over the, I guess, k-dimensional hypersphere. Yeah. I always forget. I know in like pure math, I think like, is the two sphere a sphere in 3 dimensions, or is it a sphere in 1 dimension? I always forget the terminology because I don't do pure geometry. But in this case, I mean, we have k dimensions and we have a hypersphere in k dimensions, and we're just going to spread our points out over it. Easier said than done. But the idea, right, is this goes back to kind of what I talked about in the last lecture, is that the number of points we really need to be able to estimate all the parameters in our response surface is on the order of k squared. Okay, it's actually, right, recall that the number of parameters is k plus 1, k plus 2, but divided by 2. So, okay, I'm not 100% sure why they decided to pick k squared plus k. I assume it's because it's roughly twice what you need to estimate all of the parameters in your model. But the idea is we just take this number of points and we spread them out over the sphere uniformly. And what that means is that they're as far spaced apart as possible. You can imagine it like I have a bunch of little, I guess, electric charges on the sphere, and they all repel each other. So they all want to be as far away from each other as possible. And so they spread themselves out uniformly. The easiest would be, I guess, in 2 dimensions. In 2 dimensions, we have 6 points because 2 squared is 4 plus 2 is 6. And what we end up with is a hexagon, if I can successfully draw a hexagon, something that looks like this. Because we would want them to be spaced out as much as possible in 2 dimensions like this. So, I should say, also need to replicate the center point at least once. Now, there's a couple problems with this. Problem one, finding the points is hard. Problem two is often requires many different factor levels. And that can be troublesome. Not always, but that is something that should be considered in a response surface design. Again, it's not always hard to change your factor levels, but sometimes it is, and you have to be kind of aware of that. But roughly, that's more or less the whole point. You can also nest these together. So you can nest these together to have a better fit of your response surface. And what I mean by nest is that you can basically take one of these uniform shells and then you can put another bigger one around it. So the example in 2 dimensions, of course, is I could take my hexagon here in 2 dimensions, and then I can basically draw one bigger hexagon around it. It doesn't have to be the same orientation, but I'm going to make it the same orientation just because it's easier for me to draw. And then it looks like a bunch of points emanating out from the origin. And then I have a bigger circle here. That's not a very uniform shell design, but it's, roughly what's going on here, right? And then we would have a center point. And again, you can actually imagine that what you have is you have these lines emanating out of the origin where our design points lie. Now, we can always take this to higher dimensions. It's really hard to draw, so I'm not going to draw that. But roughly, yeah, you could imagine this as nested spheres or nested hyperspheres. Now, I guess okay, we'll just add a couple fun facts, and then I think we will conclude this lecture. I still have time. All right, fun facts about these designs. Well, we've already had a lot of fun facts today. We have just a couple more to add. The Box-Behnken and the central composite design with alpha equal to root k are also spherical. This can be seen by looking at all the design points. In the Box-Behnken design case, what we would have is we would have design points that look like -1, +1, and then the rest of the entries are all going to be zeros. So in the example that I did above, you could have different settings. But in this case, we would have something that looks like this, where the distance to the origin is just root 2. It's 1 plus 1. It's the square root of 1 squared plus 1 squared, which is root 2. In the CCD case, the distance to the origin is root k. So it does change a little bit. I mean, I guess if we had more factors, if we had, say, a Box-Behnken with 2 to the 3 or 2 to the 4, then you would have a square root 2 or a square root 4 distance to the origin. Whereas in this case, the CCD, in this case, it's just root 2. Whereas our central composite design would have a radius, the sphere would have a radius of k. That's another thing you have to do for the uniform shell design, is figure out how far to space apart these, or how big the radius should be for your uniform shell design. There's a lot of like subtleties that you have to figure out how to select when you do these. Oh, and one other fun fact, the k equals 3 uniform shell design, USD, not US dollar, but uniform shell design, is equivalent to a Box-Behnken design. So that's kind of neat. That means when k is equal to 3, that means we're working in 3 dimensions. Our uniform shell and our Box-Behnken happen to be the same thing. Well, I should say there is a Box-Behnken design that coincides with the k equals 3 uniform shell design. But yeah, so basically, what do we take away from all this? Response surfaces, they're kind of neat. We're trying to fit quadratic surfaces to our data. We need enough data point and carefully chosen data point in order to estimate all of the parameters in our model. And we have many ways to do that. The easiest one, coming from what we've learned in the past so far, is the central composite design, because it naturally follows from what we've learned in this course. But there are other methods. There's Box-Behnken, there's uniform shell. There are other ones out there as well. I'm not intimately familiar with all of the details of each of them, but the point is that you just have to make sure that you choose enough points carefully to estimate all the parameters, but not choose too many points, or else you're just being wasteful. And we don't want to do that because, again, data points take time, they take money, they take effort. So let's keep our sample size as small as possible. This is the anti-big data course, of course. So we're going to do an example of this to try to get an idea of how you would use response surface in the real world for some real world data. But we're going to do that in the next lecture.